mechanics, and I wanted, you know, it's very elegant, and it kind of matches my love for functional programming. It's in that same spirit. So put these two things together. Clear, precise, elegant denotation, idea of continuous time. Those are the only things that ever mattered to me about functional reactive programming. That's what I meant by it. So, all right. So the consequence is that FRP has deterministic continuous concurrency. I'm putting concurrency in quotes because concurrency often is an operational notion and involves non-determinism and you know, non-deterministic interleaving of side effect in computation. But this computation can't be interleaved because it's continuous in time. Right? There's no room to interleave anything, and for the same reason it's deterministic. So I can't interleave, I can't interleave non-deterministically. So it's a really unfortunate name. I didn't pick this name, Paul picked this name. It ended up being sort of catchy, but in a way I regret because very widespread misunderstandings. There's something that people call FRP that they're excited about nowadays, but most of it lacks the two things I care about, which is precise denotation and continuous time. So that's a warning. If you read FRP, they won't mean what I'm talking about, probably. Byron?
By continuous, what do you mean?
No, I mean the reals. Oh, I'm going to answer that question on the next slide. Thank you. All right. So this is what FRP always was and still is to me. There's one central type, which is behaviors, and that type has a meaning. Okay, so it's a type. It's a parameterized type. Behavior of A, and has a meaning, which is behavior A means a function from the reals to A. Okay, the really, really reals. Infinitely precise. And obey all the laws that the reals do. Okay, so that's the model. It's very simple. And everything follows from there. So if I take this model, in my previous example, I started out by suggesting an interface, and then looked at its meaning, and then kind of guessed a representation, and luckily it worked out. Well, if it didn't work out, I wouldn't have shown it to you in the limited time. And then kind of retroactively, I looked back and said, oh, how does it match a standard algebraic abstraction? Now I'm going to turn it around, and this is what I actually do, which is to say, I look at my denotation. Where do I go with my denotation? I just ask myself, what does this thing mean? What are dynamic values? What are things that change with time? What are functions? And what is time? It's continuous. It's the reals. Now maybe there, you know, another perspective, a quantum perspective or something, but it's nothing like what people do with discrete time. Okay. So instead of me picking an interface first and then trying to rationalize in terms of existing abstraction, I'm going to do the reverse. I'm going to say, given only the model, I'm going to deduce the API. Not all of it, but almost all of it. Okay? And I could have done the same with the linear transformations. And we'll do it here. So, how do I deduce the API? I may ask myself this question. What standard algebraic abstractions does the model inhabit? So first I say, it's to me the one central meaningful question, which is what does it mean? And the second one is that, given what it means, what algebraic abstractions does the meaning inhabit? That's going to tell me what algebraic abstractions the representation will inhabit, and tell me exactly what the implementations have to mean are really correct. So, I think that's good.
So, where does this R come into the picture? Like, it represents time.
Yes.
Why, like, what the foundation? Why R should be the name of time?
Why did I pick R for time?
Yeah.
Huh. I knew that I wanted to represent time-varying things, and you know, I was particularly interested in computer animation. I knew that I wanted to represent time-varying things in a way that was natural for the thing, not cluttered by computery notions like discreteness and finiteness. Okay? So that was kind of a hunch. If I had gone down the other route, I would have found out that the results are actually quite complicated. So it's maybe a little counterintuitive, but my considerable experience tells me that if you choose your model to be finite and or discrete, it's going to be much more complicated than if you choose it to be infinite and continuous. It'd be much more complicated to say what everything means, and won't have useful laws. Okay? So the continuous model gives me some very nice, simple behavior, and it matches my intuition about time. So it's sort of natural for that. I enjoy the fact that it's so different from what a machine-oriented thinking would suggest, because I try really hard to be the programmer and not the programming machines.
Just to be clear, you have the model, and then that's the meaning function, right? The model is the second part, the output. Is that right?
Yes, thank you. Thank you very much. Thanks, lady. Yeah, appreciate that.
Oh,
Yeah, so I'm really showing two things here, the model and the meaning, so I abbreviated. I'm just noticing I'm running out of time here. Okay, so what's standard abstraction? So this is a key to ask this question. Come up with a model and then ask, what abstractions does the model inhabit? Now, I'll try to inhabit those abstractions in a way that's consistent. And what I mean by consistent is those semantic morphisms hold. Okay, so here we go. Functions are monoids, functors are applicatives, monads and comonads, and a few other things. So that tells me, that gives me an API, right? I implement these, I don't know, 20, 17 something methods, and exactly what they have to mean. Now it leaves one thing out, which is time itself. Just like before, I had like scalar multiplication. That didn't come from the algebraic abstraction. That was the value added, the one little piece that we added in addition. Here, the one little piece is time. The thing I call time in FRP. All right, so now, using this homomorphism, this same sort of style, we can derive what the meanings of these type class instances have to be. Okay? I'm low on time, so I'm just going to kind of flash them. An interesting thing is that it took me many years to realize what I was doing in designing FRP and other libraries, but when I did figure it out, I went back and my results exactly agreed with what I said the semantics was in 1993 or 5 or something like that. So now I know why that was exactly the right choice. It didn't just work, it was inevitable. Monad works also, comonad, there's a nice little solution. Yeah, actually some tending to skip by it quickly because it brings up an interesting question that I want to talk about in a short time. All right, so I also applied these ideas to image manipulation. I did a highly optimizing code-generating implementation of functional image synthesis and manipulation. It's exactly the same principles. I asked myself, what is an image? I considered a lot of things, and the answer I came out with is this. The meaning of an image is a function from R2 to A. It's quite similar to the meaning of a behavior. So images are infinite and continuous. It's not a habitual computery choice. It's to me was a natural choice. And then, of course, my job is to also implement it with finite discrete tools. Okay. So, ask the same questions. Given the abstraction, given the model of what abstraction is it, and I get the same sort of answers, not coincidentally. And from there, we know what it means to correctly implement this API. I want to stress something. It's super important to me to take this denotative approach and ask myself what it means independent of any operational notion. I worked in computer graphics for years and years, and we were people, and what I heard over and over was, well, there's going to be this graph kind of thing. I'm doing computer graphics, we've got some kind of graph, like a scene graph thing, and it's got some kind of transformation nodes, and there's going to be some kind of walking. And that's how they think of these libraries, but it's so important not to. So whenever I hear people talk about FERP and graphs in the same sentence, I just feel awful. Because it was critical to me to not make that confusion of the meaning with the representation. For a lot of reasons. One is for mental clarity, the simplicity of it, but also because I implemented these things in radically different ways. Sometimes I do code-generating implementations, I generate GPU code. Sometimes I generate radically transformed representations. So because I know what the meaning is, not in operational terms, I can explore radically different implementations and know exactly what it means to be correct. If I thought about these things in traditional programmer terms, like there's going to be a graph and so on, I could not have explored those alternative representations. I would have made some poor choices in the API, but I would have also crippled myself by thinking of them with particular operational bias. Okay, so recently I talked about memotrise. You can look up the paper, I'll give you a reference. But the neat thing about this example is that the meaning function has an inverse here. And whenever the meaning function has inverse, it's particularly straightforward to derive correct implementations. So, just winding up. A little bit over here, apologize for that. So try to share with you a methodology that's deeply important to me, and I think it's something that we are uniquely positioned to be able to apply to get libraries that are elegant, they're precise, they're sort of compelling, a nice fit. That's a more subjective point. It frees us from kind of complexity that is from operational concerns, and in doing so allows us to think about very different models of implementation. Fits into a nice ecosystem that supports standard algebraic abstractions. Importantly, it's free of abstraction links, and more importantly, it tells what that means, what it means to be free of abstraction links, and it accomplishes it. And then laws are effortless. And also it often gives a sort of principled way of deriving the implementation of the calculation. Okay, here's some references. Again, I'll post a link to this paper so you can follow up and email me and ask me questions. So I'm always interested in talking about this topic. All right, thank you.
Let's take time for a few quick questions. Sorry.
So the one thing I was a little confused about in the semantics that you gave for like behavior of A is where did in your implementation? So like you picked all these like algebraic structures that it needed to apply to. Where did the continuity go? Where did R go?
Where did R go? Yeah. So in something I did show you, which is time transformation. So just as when we're working with slow wave libraries for space, like images, do 3D, that kind of thing, and very important operations, we want to compose these things in powerful ways. So some important operations are transformations in space, scale, rotation, that kind of thing. If I'm talking about things that vary with time, and I want to do it in a modular composite way, then I want to be able to have transformations on time as well. So there, we have to know really what time means. If time is discrete, which is a choice that people make over and over, if time is discrete, time transformation becomes very awkward in the same way that space transformation becomes awkward in a spatially discrete moment. So most of the operations work for discrete time. It's very important to me to talk about continuous because for two reasons. One is that it's darn useful and it lets us program in a modular way. It's important for the same reason that laziness is important. It's exactly the same reason. Laziness matters because of modularity. Strictness breaks modularity. That's what the paper, Life Functional Career matters. That's what it's about. Continuity is exactly the same thing. See, I want to produce an infinite data structure because that way I don't have to assume what finite subset you're interested in. If I did assume, it would be modular, it would be as reusable. Modularity means I make as few assumptions as possible and that still give you all the information you want. So I give you more information than you're going to want. I give you infinite information. That's why we have laziness. Continuity is just the next step. So it's saying not just have infinitely many, but have infinitely dense. Because I don't know where you're going to look. I don't know when you're going to look in time or where you're going to look in space. That's why continuity matters. I also have a blog post called Reality Continuous Time Matters or something like that.
With reference to your question about the graphs, in computer graphics, most of the existing systems, they always use scene graphs, like you're saying, and their limitation is always that, they try to orthogonalize behavior and then the number of nodes, and they always have a limitation of the nodes. So from a perspective of modularity and extensibility, there's a huge problem in that, right? But I wanted
it's basically a language that was designed in non-living language, so it doesn't have a good type system, it doesn't have parameterization, it doesn't treat types, it doesn't polymorphism and so on.
But separate of that, for problems that are inherently dynamic and they're highly unstructured, right? Are you talking about the same, because what you're saying is when you see something as a graph, like if you're operating on a device that's very good at arrays, for example, like GPUs, then you want to restructure this, and if you're doing it in your compiler, that makes perfect sense. But if you're operating on a data structure that is very unstructured, right? So are you thinking as reimagining how you're storing your
Okay, so I think the question is around optimization.
No, it's like you said when you see graph, people talk about graphs, you question, are they thinking in the right way?
Are they already starting with a kind of very unfortunate operational bias that hinders their API development and the ability to implement efficiently?
So what do you think is an alternative if the domain itself has things that is very unstructured? You're storing, you have collections of items that are very unstructured.
So I do what I always do, which is I say, what does it mean? So what's a mathematical meaning that is it's elegant, precise, elegant, and it's adequate? And there may be some really important reasons to use certain data structures and match something to the machines I'm using, but none of that I want to appear in the API. All of that is abstraction. So those are all important things after I define the API.
Okay, I'm gonna have to.
Yeah, absolutely. Yeah, I'll be around for a little while after the last talk. I apologize for being late.
That's fine. But if there are more questions, I say ask Conal after the talk, and let's just take a quick few-minute break. And next we'll have Greg Weber talking about getting things done with Haskell. So, thank you very much.
If you have trash, put it in the trash bin. Not the recycle bin.